Hi, I am Sanjay Patel. In this lecture, we are going to take few more examples of ideals, and at the end of the lecture, we'll note some important things about ideals. So to start with first one, prove or disprove that the set I is equal to Zi. You know what is Zi? It is the set of all, say, complex numbers of the form a plus ib, where a and b are integers, is an ideal of the ring C, comma plus, comma dot, that is the set of complex numbers. Prove that the set of numbers a plus ib, where ab belongs to z. These are all Gaussian integers. The set Zi is called Gaussian ring. We want to check whether it is a ideal of the ring C or not, ring of complex numbers. You know that this I is a subset of C. It contains complex numbers whose real and imaginary parts are integers. Okay. So if I start with the first thing, it is non-empty. As 0 belongs to I can say that I is non-empty set. Secondly, if I take two elements from this set I, if I take Z is equal to A plus IB and W is equal to C plus ID belongs to I, then you know very well that Z minus W is also a member of I, because Z minus W is nothing but A minus C plus I times B minus D. So it is also of the form, say, P plus I into Q, where P is equal to A minus C and Q is equal to B minus D. Both are integers, because A, B, C, D all are integers, as this belongs to I, where I is our set Zi. Okay. So this P and Q are integers because A is integer, C is integer, so A minus C is integer. B and D are integers, so B minus D is also integer. So this belongs to the set I, which is Zi. So what I have proved is, for every Z and W belong to the set I, which is Zi, implies Z minus W belongs to Zi. So that is, we can say that Zi is a subgroup of the group C, comma plus set of complex numbers. Let me write properly. Is a subgroup of the group of complex numbers C, comma plus. Okay. The next thing you want to check it is that condition for ideal. If we are given, say, some element R is equal to, let me say, instead of R, let me take some other notation. Say, let us take one element, say X is equal to A plus IB belongs to capital I, that is this set Zi, and let me take one element R is equal to, say, C plus ID belongs to the ring R, where ring R is nothing but the set of complex numbers. This is the set of complex numbers. Okay. Then you want to check whether x into r or r into x belongs to I or not. Remember, here a and b are integers. A and b are integers because this zi is a Gaussian ring where real parts and imaginary parts of any element in zi are always integers. So if I multiply this x into r, say that is a plus ib into c plus id, like this, then you know it is ac minus bd plus I times ad plus bc. But this need not be always an integer. Why? If I choose say some element x is equal to 2 plus 3i, for example, in the set I, and let us take some element r is equal to say 1 by 2 plus 3 by 2 times I, 1 by 2 plus 3 by 2 I belongs to the ring R, which is C. Then if you find x into R, then x into R is 2 plus 3i into 1 by 2 plus 3 by 2i, which gives you this into this, that is 1 minus this into this, AC minus BD. So it is minus say 9 by 2 plus I into 2 into 3 by 2, that is 2 into 3 by 2, that is 3, plus this into this, so it is 3 by 2. Okay, so that is actually 2 minus 9 is minus 7 by 2 plus 6 plus 3, that is 9 by 2 times I, which is not an element of the set I, which is Zi, because this is not integer and this is also not integer. So even though x and r belongs to I and C, I and r respectively, this x into r does not belong to I. So therefore I can say that I is not a right ideal, because remember this r is multiplied on the right hand side, is not a right ideal in C. Okay, so the set Zi is not an ideal in C. So thus I is not an ideal of C. Okay, fine. Let us take another interesting problem. Suppose we are given, say, some two ideals. What can you say about their intersection? And that if we have two ideals, say I1 and I2, if I find the intersection of two ideals, then what can be the new set? Will it be an ideal? And the answer is yes. And this follows in this new example, that if I1 and I2 are any two ideals of a ring R plus dot, then prove that I1 intersection I2 is also an ideal. That means intersection of two ideals, any two ideals, is always an ideal. Okay. So let us prove this. To prove that something is an ideal, we must check three conditions: that it is non-empty, it is a subgroup of the given ring, and it satisfies that ideal condition. So first of all, remember that I1 and I2 are ideals here. So they contain 0 because they are subgroups with respect to addition. So as 0 belongs to I1 and 0 also belongs to I2. You understand? I1 is an ideal, so it is first of all a subgroup of R plus. So it contains the 0 element. So both the sets I1 and I2 contain 0. So I can say 0 is also an element of the intersection. So therefore, I1 intersection I2 is a non-empty set. That is our first conclusion. The second thing I want to explain here is it is a subgroup. So let us take two elements, say x and y belongs to I1 intersection I2. What I want to prove is x minus y also belongs to I1 intersection I2. Now as x and y belongs to I1 intersection I2, it is clear that x and y belongs to I1 and x and y also belongs to I2 because they are in the intersection, so it is in all the sets. This implies x minus y belongs to I1 because I1 is an ideal, so it is a subgroup, so it satisfies this condition. Same way I2 is an ideal, so x minus y also belongs to I2. It is an important step because I1 and I2 are ideals. So by the first condition of ideal, we can write this. And this means this element x minus y, it is in I1 as well as in I2. So it belongs to I1 intersection I2. Okay. So what we have proved is the second condition, that for every x and y belongs to I1 intersection I2 implies x minus y also belongs to I1 intersection I2, and that is the set I1 intersection I2 is a subgroup of the group R comma plus. So this is my second conclusion. Now to prove the last thing about ideal, that is the ideal condition for the set I1 intersection I2. So let us take one element from the ring, say small r belongs to the ring R, and one element from the given set, which is I1 intersection I2. So x belongs to I1 intersection I2. This to be arbitrary. They are given. Okay. Now x belongs to this I1 intersection I2, right? That means it is in both the sets. So x belongs to I1 and x belongs to I2. Now I1 is an ideal. I1 is an ideal. Okay. And we have two things, R belongs to R and X belongs to I1. So I can write this implies R into X belongs to I1 and X into R also belongs to I1. Okay. So this is my result number 3. Or let me, okay, no problem. Same way, similarly, I2 is an ideal. I2 is an ideal, and we are given that R belongs to R, and we also know that x belongs to I2. So I can write this implies R into x belongs to I2 and x into R also belongs to I2. By the definition of ideal, XR and RX both belong to I1 and I2. So therefore, from 3 and 4, we can say that Rx belongs to I1 intersection I2 and x into R also belongs to I1 intersection I2. Okay, so what I have proved? Thus, for every R belongs to capital R and x, for every x belongs to I1 intersection I2, I have proved that R into x belongs to I1 intersection I2, which says that it is a left ideal, and x into R also belongs to I1 intersection I2. So it follows that from the result number 1, 2 and this 5, it follows that I1 intersection I2 is ideal. Therefore, from 1, 2 and result 5, we have I1 intersection I2 is an ideal of the ring R. So we have proved that intersection of two ideals is always an ideal. But note that this result is not true for union. The above result is not true for the union, of ideals. That is, if you have two ideals, then their union need not be an ideal. That is, union of any two ideals need not be an ideal. Okay. So whenever you say something is not true, you have to give some proper example, counter example. So here I am going to consider the example of the ring of integers. So let us take R is equal to the ring of integers. I will write in short, this is the ring of integers. And the operations, as you know, they are the standard or usual addition and multiplication of integers. And we know many examples of ideals from our last lecture. So I am taking two such ideals. Say, let us take I1 is equal to 2z. What is 2z? It is 0 plus or minus 2 plus or minus 4 and so on. All multiples of 2. We know that multiples of any integer is an ideal in the ring of integers. So I am taking I1 is equal to 2z and I2 is equal to 3z. 3z means all multiples of 3. So 0 plus or minus 3 plus or minus 6 plus or minus 9 and so on. So I am taking these two sets. We have already proved that I1 and I2 are ideals. These are ideals of the ring Z. Okay. Now I1 union I2. I1 union I2 means all elements which are either in 2z or in 3z, means which are either multiple of 2 or multiple of 3. So it is either 2k or it is of the form 3k, where k is some integer. K belongs to Z. Now what I want to prove is this is not an ideal. Okay, which is very, very obvious, as 2 and 3 belongs to I1 union I2. Okay, you can note that 2 is an element of I1 union I2, and 3 is also an element of I1 union I2. But if you take 2 plus 3, then that is 5, is not an element of I1 union I2. So I1 union I2 is not an ideal. Therefore, I1 union I2 is not a subgroup, of the group Z, plus. So therefore, I1 union I2 is not an ideal. So union of two ideals need not be an ideal. It follows from this counter example. Okay. There is one more interesting problem that I am leaving it to you to show that sum of two ideals is always an ideal. So the third example, let I and J be two ideals in a ring R plus dot. Okay. Define the sum of I and J as I plus J. It is given as set of all elements of the form A plus B, where A belongs to I and B belongs to J. Okay. Prove that I plus J is also an ideal of the ring R. Okay. Let us prove. Clearly, I and J are ideals. So we know that 0 belongs to I and 0 belongs to J. Also, we can write 0 is equal to 0 plus 0. So this 0 is an element of I plus J. So the conclusion is I plus J contains something, so it is non-empty set. It is non-empty set. Okay. Now the second condition is it is a subgroup. I plus J is a subgroup. Say if you take X and Y belongs to I plus J, okay, then I can write X in the form say A1 plus B1, and Y is also of the form A2 plus B2, where A1, A2 belongs to I and B1, B2 belongs to J by the definition of I plus J. So what is I plus J? It is set of all elements of the form A plus B, where the first belongs to I, second belongs to J. So if you take X belongs to I plus J, you can write X in the form something plus something, where the first element we are writing in I and second belongs to J. So here A1, A2 belongs to I and B1, B2 belongs to J. And this implies if I write X minus Y, so it is A1 plus B1 minus A2 plus B2. which we can write as a1 minus a2 plus b1 minus b2, because the operation of addition is commutative here. And this I can write as, say, a plus b. This can be expressed as a plus b. Okay, where what is a? Where this element a is a1 minus a2, and it belongs to I, because I is an ideal, so it is a subgroup. So whenever a1 a2 belongs to I, we have a1 a2 belongs to I, so a1 minus a2 belongs to I, because I is a subgroup. I is a subgroup. Same way, b is equal to b1 minus b2 belongs to j, because j is also a subgroup. Okay, so what I have proved is x minus y is of the form a plus b, where a belongs to I and b belongs to j. So therefore, x minus y is of the form a plus b, where a belongs to I, and b belongs to j. So therefore, the conclusion is x minus y is a member of the set I plus j. So finally, I can say, therefore, for every x and y belongs to I plus j, we have x minus y belongs to I plus j. So I plus j is a subgroup. Therefore, I plus j is a subgroup of the ring R comma plus, or rather the group R comma plus. So this is my second result. The first result is what I have shown is I plus j is non-empty, and here I have proved that I plus j is a subgroup of plus. Now the next thing is the condition for ideal. So I am taking one element, the x belongs to I, and one element R belongs to the ring R. These are given. Now as x belongs to I, and I should not take I should take I plus j. I wanted to prove that I plus j is an ideal. So I should take one element from the set I plus j and one element from the ring R. These two are arbitrary elements. Now as x belongs to I plus j, I can write x in the form a plus b, where a belongs to I and b belongs to j by definition of I plus j. Now, if you find R into x, then what is R into x? That is R into a plus b, which we can write as R into a plus R into b by the left distributive law in the ring. Remember, everything here finally are elements of the ring R, original ring. So we have R into x, it is of the form, say, p plus q, okay, where p is equal to R into a, and it belongs to I. Why? Because I is ideal. So let me write, say in more detail, just let us mention that p is equal to R into a, and q is equal to R into b. So now I is ideal, and R belongs to R and A belongs to I. Yes, we have taken A belongs to I and R belongs to R. So I can say that R into A belongs to I, and that is P belongs to I, because I have taken P is equal to R into A. Similarly, as J is ideal, as J is ideal and R belongs to R and B belongs to J, I can write that R into B also belongs to J. R into B belongs to J, and that is Q belongs to J because J is ideal. So thus what is proved is the element R into X is of the form P plus Q, where P belongs to I and Q belongs to J, and that means Rx belongs to I plus J. So what is the final conclusion is, for every R belongs to capital R and for every X belongs to I plus J, we have R into X belongs to I plus J. And similarly, we can prove that X into R also belongs to I plus J. Okay, so what we have shown is our third conclusion, and from 1, 2 and 3 it follows that I plus J is an ideal. So therefore the set I plus J is an ideal of the ring R. Okay, so we have seen some interesting examples which gives you the idea that how one can construct more ideals from the given ideals. The first way is, if you are given any two ideals, then you can take the intersection, then it is always an ideal. And remember that result about intersection is also true for any number of ideals. Means you can generalize that result and say if I1, I2, I3 and so on up to In are n ideals, then the intersection is also an ideal. And the third example says how to construct a new ideal from the given two ideals by adding the two sets in this manner. And this is a useful example. And finally, we just note some important things about ideals is that an ideal is always a subring of a given ring. So some few remarks about ideals. First thing, every ideal is, or let me write this way, every ideal of a ring R is always a subring, which is very obvious from the definition of ideal. What do we want in the subring is, it is subgroup as well as close with respect, close with respect to multiplication. In fact, subring is nothing but a ring only. So you need to prove only two conditions, as you know, and both the conditions are there in the definition of ideal. So it is obvious that every ideal is a subring of R, but the converse is not true. A subring of a ring R need not be an ideal. So the converse of result, or the remark 1, is not true. Okay, so subring of a ring R need not be an ideal. This I can explain by one counter example. Say, what I have to do is I have to find a subring in a ring, and it is not an ideal. So consider the ring of real numbers, the ring R plus dot of real numbers. So this I am taking with respect to usual addition and multiplication of real numbers. And consider the set I. Let me write this way. Consider the set of integers s equal to z, and is subset of R. Okay. We know that this z is a subring. We already proved that. We know that this z is a subring of R, is a subring of the ring R. Okay. But it is not an ideal. This set Z is not an ideal. Why? If you take one element, say x is equal to say 3, belong to this set I equal to say Z, and if I take R is equal to say root 2, belongs to the set R, then R into x, that is root 2 into 3, is not a member of I, that is the set Z. So Z is a subring of R, but not an ideal. So therefore this Z is not an ideal, in R. Okay. So ideal is always a subring, but a subring need not be an ideal. So we have noted two important things. Every ideal is a subring, but a subring is not an ideal always. The next thing I want to mention is in any ring, the two sets are always ideals. In any ring, R plus dot, the sets I equal to say singleton 0, and if I take I is equal to the ring R itself, are always ideals of the given ring, of the ring R, and these ideals are known as called improper ideals. So very, very important statement, or I can say definition of improper ideals. The singleton 0 and the whole ring are always ideals, and they are called improper ideals of the ring R. They are also called trivial ideals. Another word we use, trivial ideals. They are called trivial ideals of the ring R. Okay. Any other ideal of the ring which is different from singleton 0 and R is called a proper ideal. So let me write that as the next important remark. If I is any ideal of a ring R, such that I is not equal to singleton 0 and I is not equal to the whole ring R. Okay. Then such an ideal I is called a proper ideal. Remember, this will be important thing in our last topic about this lecture series of abstract algebra about rings is called proper ideal. Okay. So, what is a proper ideal? An ideal which is different from singleton 0 and R. And remember that all other ideals are lying between this and this. So that is singleton 0 is subset of I is subset of R, and it is not equal to R and it is not equal to R. Okay, so this is called proper ideal. It's called proper ideal. So every ideal which lies between the singleton 0, which is the smallest ideal, and the largest ideal is the ring R itself. So any ideal which is different from these two is called proper ideal. Okay. So this is something very important thing, and we are going to prove in our next lecture that if you have a special type of ring, then it has no proper ideals, and we'll discuss the converse also in that case. So till then, goodbye. Thank you.